For this week, our objectives include the following. Firstly, we'll create design modules to model the design and a test bench module to enable testing of the design module. A Verilog module is the main building block in Verilog. Next, we look at instantiation of modules. This is the way in which Verilog allows a module to be used. We introduce and use two important types in Verilog, the wire type and the reg type. Finally, we create a design using a simple hierarchical structure. Modules are the key building block when designing using Verilog. These are blocks of Verilog code which represent the functionality for designs. You can think of a Verilog module as a block having inputs, outputs, and bidirectional I/O. All Verilog designs are constructed using modules. Here is an example of a simple combinational logic circuit or a logic block. There are 3 inputs and 1 output. To code the Verilog module that describes this logic block, we start by considering the inputs and outputs only. This is the proper way to start defining a module for a logic block. So in our case, we'll just look at the inputs A, B, and C and the output G. To begin our Verilog module, we use the keyword module. This is a reserved word in the language and can only be used to define the start of a module. In our example, all keywords are shown in bold on this slide. Following the keyword module is the name of the module, in this case and/or. This is an identifier that you, the designer, use, and it is best to use a name that describes the module, in this case and/or. No spaces are allowed in the identifier, and in Verilog an identifier is a name that's used to label modules and other objects that we need in our designs. An identifier always starts with a letter or an underscore character and can be followed by alphanumeric characters, underscores, and the $sign. An identifier cannot start with the $character. The length of an identifier is tool dependent and is not defined in the Verilog language. Also note that identifiers are case sensitive, meaning that the identifier and/or starting with a capital A is different from the identifier and/or starting with a lowercase a. There is another way in which identifiers can be defined, and it's known as an escaped identifier, in which the identifier begins with the \/ character. This is not relevant for us in this course and is only needed for compatibility with some third-party tools. So all our identifiers will start with a letter or an underscore. In defining our module, the next part is the port list. This is a comma-separated list of identifiers enclosed in brackets. And the identifiers used are the labels we've given to the inputs and the output. In this example, A, B, C, and G. And the list of identifiers are separated with commas. The comma-separated list is enclosed in brackets, and following the closing bracket, we have a semicolon. The order of the port identifiers is not specified in the language, so if you want, you could have G first, followed by A, B, C. In practice, you stick to a convention, and for our example, we have the inputs first. So if you are developing a design with lots of modules, all modules will list the inputs first, and this avoids confusion when you or team members are reading code and using modules. So at this point in defining our module, we now have specified the module name, which we've selected to be and/or, and we've specified the inputs and outputs. All modules end with the keyword end module. This is a single word with no spaces. Our next step then is to specify which of these identifiers are inputs and outputs. And to do this, we use the keyword input and the keyword output. So starting with the keyword input, we follow it with a list of the inputs separated by commas and terminated with a semicolon, and we've only one output, in this case just the output G. In addition to inputs and outputs, there are different types for ports. This declaration is a declaration that all the ports A, B, C, and G are of type wire, where wire is a type specified in the language. And it turns out a good way to think of the wire type is to actually think of a physical wire that you would have encountered in your first year digital modules. At this point, we've only considered the interface, dealing with the inputs and output for the module, and the last part of a module definition is to address what's actually happening inside the module. And in this example, we can do so with this statement. It's an assign statement, and it involves an expression which, when evaluated, assigns a value to G, which is our output. Verilog is free format. This means we can use spaces and new lines to neatly format our code, making it readable. We've explicitly declared A, B, C, and G to be of type wire. In the Verilog language, by default, ports are of type wire, and we do not need to explicitly indicate that A, B, C, and G are of type wire. So if you want, you can omit this declaration. The complete section of code shown in yellow is an example of a module definition. When coding the module, ensure that you include the semicolon at the end of the port list. And note there is no semicolon following the in module keyword. A more compact means of defining the same module is shown here. When creating the port list, we can specify the input and output keywords as part of this list by using those keywords before each identifier or before a comma separated list of identifiers. For example, A, B, C can have the input keyword preceding that comma separated list, thereby indicating that A, B, and C are inputs. And the output G can have the keyword output preceding it, indicating that G is an output. This feature was not available in earlier versions of the Verilog language, but its addition provides us with a compact way to create the port list. Older textbooks and documentation use the syntax on the previous slide. This form of the port list shown here was introduced in the 2001 update of the Verilog language. Another point to note regarding modules is that they cannot be nested. What we mean by this is that it's not possible to define a module inside a module. The purpose of modules is to define models, and a model is a way in which we can describe the functionality or the behavior of a design. And in the example here, we say that we are modeling a simple combinational logic block. Now that we've seen how to define a module, what next? Well, all design modules must be tested. A design module contains the interface using a port list and the functionality or behavior for that design. In order to test a design module, we must provide test inputs and monitor or observe the outputs of our design. So far, we've used Verilog to model our design, and it turns out that the same Verilog language can also be used to describe our test steps. And the test steps enable us to drive values onto the input of our design that we want to test, and we can monitor the output with our test code. This is an important idea, that the same Verilog hardware description language that we use to describe or model our design can be used to provide the test steps to test our design.